Okay, how do we cluster? That's first question. Second, how many clusters should we have? So that's the second question. And that's what this lecture is going to be. This entire session is going to be about answering these two questions. Now, with that background, let's take a look at this diagram once more. Take a look at this diagram. And in you see in cluster 1, I have highlighted 2 data points by drawing a square around them. You could also see I have one data point identified in cluster 3, one in cluster 2, and one in cluster 4. Right? I identified a few data points. Now, if you see these 2 points in cluster 1, they are closer to each other than to any point in any other cluster. Right? Than to any point in any other cluster. These 2 are closer to each other. That's one defining characteristic that you can see. Right? Like, for example, this point is closer to this point here than to this point in 3 or 2 or 4. Okay, that's one thing. Second thing is, let's focus on these 2 clusters, these 2 points that I have marked, one in cluster 2 and one in cluster 4. Okay. Now, I have drawn these things as some kind of a circle or an oval. Therefore, you can find the geometric center of these areas, right? So, we will call this a centroid. Okay, we'll call this centroid. Now, if you see these 2 points, the one in cluster 2 and the other one in cluster 4, though they are very close to each other, the one in cluster 2 is closer to the centroid of cluster 2 than to the centroid of any other cluster. Likewise, the one point that I have highlighted in cluster 4 is closer to the centroid of cluster 4 than to the centroid of any other cluster. So that's the second point that comes out, right? We expect all points in a cluster to be closer to each other than to any point in the other cluster. That's what we expect. But in addition to that, a more stronger point is that a point in a cluster is closest to the centroid of that cluster than to the centroid of any other cluster. That's another property we are understanding here, deriving this. These are some properties. We are going to fix this and define some quantities later to actually quantify how good our clustering scheme is. Okay, that's well and good. Why do we decide, or how do we decide that all these points lie in a single cluster? Okay, all the points in cluster 1, for example, how do we decide that all these points lie in cluster 1? So, intuitively, if you look at this, okay, as I told you, the points in a cluster are close to each other than to points in other clusters. Right? Now, what does that close to each other mean with the double quotes? So, how do we define this closeness? Okay. This closeness, we also use another word called similarity. Okay. Points in cluster 1 are similar to each other than to any other point. Points in cluster 3 are similar to each other than to other points in other clusters. So how do we define similarity? If we define similarity in some sense, then we can identify clusters. And similarity, as I told you earlier, is nothing but how close these points are to each other. Closeness of a point. That's all. So closeness of a point means, as you can see in a two-dimensional plot like this, 2 points, how do I say whether they are close to each other? I just find the distance between them, right? I just find the distance between them. And that is the main property we are going to deal with. Okay? Distance between 2 points. So I have this two-dimensional plot, x1 and x2, and I have 4 points denoted here. So in terms of, if you look in this, you can easily identify that points 1 and 2 are close to each other, okay, than to any other points. Then between point 2 and 4 and point 3 and point 4, it's not clear which is close to each other, right? So all we have to do is, if you want to find the point which is closest to 1, we find the distance of all other points from this point 1 and identify the one that is closest to itself, right? So 1 and 2 are very close to each other. Okay? This distance we have to find. That's all. If you can calculate this distance, the problem is solved. We find a similarity. There is another kind of similarity that we use, and this is useful only when each dimension is standardized, or let me take a step back, okay? What I want to say is that in this case, I have a two-dimensional plot, right? Only I have two variables, 2 dimensions. And every point in this two-dimensional plot, okay, every point in this two-dimensional plot, I can represent as a vector, right? So give me just a minute, please. Let me satisfy my OCD a bit.
Sir, one quick question.
Yes.
So some of the data points in the earlier plot, you you highlighted a square, right? What are those data plots, and why did you highlight in a square
Just
as
example
against the
points. Just example points. So I just want to say
example?
why these 2 points
Random,
are in cluster 1, random.
random. Okay,
Why
got it.
these 2 points are in cluster 1? Why not this point not in cluster 4? Because these 2 points closer to each other, and both of them are closer to the centroid of cluster 1 than to the centroid of any other points.
Okay. See, just a follow-up question there. Sir, if you draw another cluster, which is like the sixth cluster, which is like, say, the one between 5 and 1,
Yeah.
then there will be some of the, like the distance considerations you mentioned, those would be challenged, correct? Or,
If this, see, for example, we probably definitely can have one cluster here. I'm hoping. Okay. And let me see whether I can get the same area transparency. 5. Okay. So if I have another cluster like this, okay, that's well and good. Who is what is that to prevent me from having another cluster like this? All the points in this cluster are closer to each other than to any other points in other clusters, and they are closer to the centroid of this cluster than to the centroid of any other cluster.
Okay, yeah, in this case, yeah, makes sense. Okay. So if if it's very close, then that's when, I mean, that doesn't meet the criteria of kind of creating another cluster, I guess, right? You're
Yes.
saying.
Yes.
Okay.
So for example, even this could be another cluster. I am thinking even this could be another cluster. Okay. So we may have one other cluster. It is possible that we could have one other cluster like this. Okay. Of course, except that the clusters don't overlap. Okay. So one other cluster like this is possible. Okay. It's possible.
Got
We
it.
have to check. How do we
Got it.
check? I mean, this is visually I'm doing this. Okay. But we
Mm,
can do it objectively.
understood.
How do we do it objectively? By looking at these distances. Okay. And we will
Okay.
come to the algorithm in a short while. What algorithm you are going to use?
Okay.
Sir,
Thank you, sir.
sir, just another question here is if you've covered already in another class, I'll look up. But how is the centroid identified?
We'll come to that again.
Okay.
It's not done yet. We'll come to that.
All right. Thank you, sir.
Yeah, sure. So I'm just throwing out some names here, which we will discuss in a short while. Okay.
Professor, a quick question here. I know we started this session with saying that clustering is two-dimensional, but can it be three-dimensional or multi-dimensional, or does that make it very complex?
Multi-dimensional, yes, it will generally be. I'm showing this example in 2 dimensions because visually it's easy to show. That's all. Just a demonstration. It's not, clustering is usually done in multiple dimensions.
Got it.
That is why we need to go for these kinds of objective measurements, objective measures, so that we don't have to worry about visual judgments.
Okay,
right?
Got it. Thank you. Thank you.
So, thing is this: any data point in a multi-dimensional space can be represented as a vector, like how we represent a vector in a 2-dimensional plane like this. So, if you can imagine multiple dimensions, all intersecting at one point called the origin. From the origin to that data point, that's called the vector corresponding to that data point. Okay, so that's how we represent vectors. Right now, so we have these 4 vectors here, 4 data points represented as 4 vectors. Okay, let it be. Now, so I told you earlier that distance between 2 points can be used as a measure of similarity. It's very well and good, easy. But more than that, another very cost-effective measure is what is called angle similarity. Now, finding the angle between 2 vectors. However, here is the catch. This angle similarity is meaningful only if all the vectors have the same length. Right? Think of a sphere and all points in the data are on the sphere. If that is the case, then we can use the angle between 2 vectors as a measure of similarity. Whereas if we have data points which have vectors of different lengths, like for example 4 here and 3 here, okay, then angle similarity does not work. Now, why am I even talking about angle similarity? The reason is there are certain situations where each vector is each vector has the same length. Okay. When does it happen? it happens in your next course when we are talking about deep learning, especially when we are talking about some representation of text. Okay, all these representations, this is called encoding. These different encodings we are going to use for text, they will all have a value, they will all have a length, this vector length of 1. We should probably tell you anything of value 1, that probably immediately should tell you that we are talking something like probability. And in fact, that's what we do. Okay, that's what we do. So we are looking at probabilistic representation, in which case the vector will be of length 1. Okay, that's what we are going to do. And in those situations, calculating the angle similarity is much easier than distance similarity. Okay? In all other cases, specifically in this course, which is a course on structured data, we will use distance similarity. Okay? That's what we will do. Okay. So what is this clustering? Identify points that are close to each other and also far from others. Okay? They are far from points in the other clusters. Okay? So how do we identify that points are close to each other? By measuring the distance, that's for structured data, or measuring the angle for the unstructured data. So let's talk about distances. Okay, distances. How do we measure distances? So again, it's only for demonstration purpose I am drawing this, but we can do it in, the idea can be easily extended to multiple dimensions. Okay, so what is this? Let's consider a data point P1 with a vector value of x11, x12. Okay, this has x11 for x1 axis, x12 for the x2 axis. Likewise, another point P2, which has a value of x21, x22. Okay, it has a value of x21 for the first axis, x22 for the second axis. So we want to find the distance between P1 and P2. Okay, so that's what we want to do. To do that, yeah, let's draw a few things. So like how we were drawing orthogonal bisection yesterday, we are going to draw these orthogonal distances. Okay? Or if you drop a perpendicular from one point to one of the axes, okay, so here is the perpendicular from point P1 to the x1 axis, find the perpendicular distance of P2 from that line. So that will be this x2, that will be x21, that's this position, and this position on the x1 axis is x11. So this is the distance. Likewise, we can calculate this distance. Okay? So that will be x22, which is this point x22, minus x12, which is this point x12. Okay? So this distance is x22 minus x12. Now it should be very familiar to you that we can easily find the distance between P1 and P2. This comes from Pythagoras theorem, right? So before that, once we know these distances, x21 minus x11 and x22 minus x12, okay, we define a quantity called Minkowski's distance, which is given by this. Okay. What is this? If see this distance value raised to the power p plus this distance value raised to the power p, the whole of them within the pth root. Okay, pth root of pth power of sum of the pth power of the distances. Okay. It's a very complex or very complicated expression, but if you look at it, it is nothing but the Pythagoras theorem. Okay, Pythagoras theorem. In fact, it is nowadays it is very well established that even 500 years before Pythagoras, there was this mathematician Pingala who had stated this theorem. Okay. So we can, if you want, we can call it Pingala theorem also. Yes, Sam, please go ahead.
It's the diagonal. P1,
Say
P2 distance. It's just a diagonal.
exactly. It's a diagonal. It's actually called the hypotenuse.
Thanks.
In the triangle world, it's called hypotenuse. If you make it a square, then of course it's a diagonal. It's a diagonal. Correct. Okay. So the Pythagoras theorem, if you see, is nothing but square root of sum of the squared differences. Root sum squared difference. That's what Pythagoras theorem is. Okay, square root of the sum of the squared distances along each axis. Instead of 2, you write p. So this is a pth power, this pth power. Instead of square root, you have the pth root, where p can be any integer going from 0 to infinity. Okay. This is called Minkowski distance. Okay.
Sir, because one point is always the centroid, it's always a 90-degree angle that gets created, is it?
No, it has nothing to do with the centroid.
Oh, okay.
Okay, all we are doing is we are finding the distance between these 2 points parallel to each axis. Okay, this is the distance between these 2 points parallel to this axis x1. This is the distance between these 2 points parallel to this axis x2. So we find those distances, square them, add them all, and then take the square root. That is the hypotenuse. That's called the Pythagorean distance. Okay, it's the hypotenuse. Now, this is the shortest distance between any 2 points. The hypotenuse defined like this, the distance defined like this. This is the shortest distance between any 2 points. Okay, but what is this distance? P. Now, instead of 2, if you have some other number, what happens? As you can see, okay, as p increases, what happens to this? The larger distance, or the, if you have more than 2, no, x2 minus x1, x2 x1 minus x1 to the power p plus x22 minus x12 to the power p plus x23 minus x13 to the power p, so on and so forth. Then, if you look at this, if you have as you increase the power of p, the larger value increases by a larger amount than the others. For example, let us say one of them is 1. Let's say this distance is 1. This distance is 2. And let's say we are talking third distance. Third distance is 3. Okay. When p is equal to 1, then we have 1, 2, 3. When p is equal to 2, which is the Pythagorean distance, we have 1, 4, and 9. See, already it's the effect of 3 is exaggerated now. Let's go to p is equal to 3, third power, okay, cubic. Then 1, this becomes 2, 4, 8, 1, 8, 27. Usage is 1, 8, 27. Now its effect is much increased. If you go to the power 4, what happens? 1, 16, 81. 1, 16, 81. Right? If you go to the power 5, then it will become 1, 32, and 405. You see that? Much. No, not 405, sorry. That will be 8 is 24, 243. 243. Okay. 1, 32, 243. So what does it do? The Minkowski's distance helps us to exaggerate the effect of the largest quantity in this sum. This is useful in some cases. In which cases? In cases when we want to find anomaly. Think about this. Why do we say something is anomalous? It's anomalous because it looks like normal, but something is very different. Right? It looks like normal, but something is very different. That's what anomalous is, right? So, for example, every day you have been purchasing something using your credit card, and suddenly today the same credit card is being used some 1000 kilometers away, right? So now that positional effect where the credit card was used, okay, that has to be exaggerated so that we can see whether it's an anomalous purchase or not, right? So this thing, this Minkowski's distance is useful to identify anomalies. You can play with the different values of p. You can play with the different values of p, and you can get so you can treat p as a hyperparameter and see what values of p actually helps you solve the problem that you are dealing with. When p is equal to 2, we have Pythagoras theorem that tells you the shortest distance between any 2 points. This is what we want, right? Shortest distance, similarity, right? Similarity. Then there is another distance called Manhattan distance. Manhattan distance is when p is equal to 1. That is like walking from p1 along these orthogonal distances, right? Along this one side of the triangle and the other side of the triangle. If it is multidimensional, 1, 2, 3, right? 1, 2, 3, multidimensional. Okay, so that's what this Manhattan distance is. Why it's called Manhattan distance? It's basically because apparently I do not know this. People who have been in Manhattan or who live in Manhattan or who work at Manhattan can vouch for this. It's a very well designed place where the streets cut across in a perpendicular direction for the most part, right? And so people have named it Manhattan distance. Anyway, so we have distance defined using these 3 ideas. Minkowski distance, which helps you magnify the effect of that one variable which has a larger difference between the 2 points. Euclidean distance finds the shortest distance between the 2 points. Manhattan distance is what is the total distance you will have if you walk along each of the axes from point 1 to point 2. Okay, that's what Manhattan distance is. Is Manhattan distance going to be of any use? Obviously, yes. It's called a minimum grid distance, okay? And it has very important use. Okay? And where it is used when we are dealing with categorical or binary variables. When we are dealing with categorical binary variables, that's when we use Manhattan distance. Okay? Where do we use Euclidean distance? We use Euclidean distance when we have variables, continuous variables, not variables that have continuous values, like age, salary, quarterly returns, number of items returned, those kind of variables. We can use Euclidean distance. Okay? Manhattan distance for categorical variables. Minkowski distance is when you want to exaggerate the dimensions that have the largest difference in their values between 2 points. Okay, so that's when you will have Minkowski distance. Okay, let's folks, please give me one minute, please. Something is bothering me. Please give me 1 minute. Thank you. Okay, so let's talk about something we have to be careful about when we deal with Euclidean distance. Okay, here is an example of 4 people. Okay, we want to see whether any clustering can be formed in this group. That is, we want to see whether any one of these 4 persons, any 2 or 3, are similar to each other. Okay, so how do we define similarity? We have to find out what is the distance between one point from another point. So between from A to B, A to C, A to D. So if you look in here, A and B, okay, are similar in height, but different only in age. Okay, so the distance between A and B will be only 40 minus 35, which is 5, 5 squared, which is 25, 25 square root of 25 is 5. So distance between A and B is 5. Distance between B and C, again, you see this is a 5 plus 190 minus 60, 160, that's 30. 30 squared is 900. Okay, 900 plus 25, 925. Square root of 925, that's about 30.4 or something like that. Okay, that's about 30.4. So B and C distance is 30.4. A and B, the distance is 5. C and D, the distance is again 5 because they have same heights. Okay, how about A and D? A and D, they have different heights and different ages. So 5 plus 30, so again 30.4 or something like that. Okay, so we have 2 points, that is A and B, that are close to each other. Then C and D that are close to each other. A and C that are farther from each other because 35 and 35. Okay, they are same age, but heights 30, 900. Right? Likewise, B and D 40, 40, 190, 169. So it seems like let me try to show what I am expecting. No? Okay, so let me do slide. So if I were to draw age along this, okay, and then height along this, right, it looks like I have 2 points, that is A and B, A and B that are like this, and A and C that are like this. Okay, so let me write where is insert text box. So A is 35 and 190, and then we have what is in B is 40 and 190. So we have B to be 40 and 190, and we have C to be 35 and 160, and then D to be this. Okay. So this is what we seem to be having. Let me make this. Right? Right? So if y is age, if this, let's say this is age axis, Control C, Control V. So let's say this is age. And this is height. Height in centimeters. So this is how it looks like. So looks like A and B are closer to each other, and C and D are closer to each other. So we have these two clusters. We might be having these two clusters. A and B as one cluster, and C and D as another cluster. Okay. Now, what I do is I do another small trick. What I do is I change the units. Okay, units of height. Who measures heights in centimeters? You know, all these people outside of US, only they do. In the US, we don't measure in centimeters, we measure in feet. So 190 centimeters is 6.232 feet. Likewise, 160 centimeters is 5.248 feet. Okay, so let's convert this and see what happens. If you now look at this particular diagram, okay, and this particular data, and then plot this data now. Okay, now you see what happens is this. We get a situation something like this. You see, A and B, they have the same height value, but they have a distance of age of, or did I change this? Oh, I did that. I did a different thing. A and B. So this should be, excuse me, this should be height here, and this should be age here. Okay, because the age are different for A and B. For A and B, the heights are the same. Okay, that makes sense. Okay. Now, if you see, when I change the units, the clustering now seems to have changed. A and C seem to be in one cluster, and B and D seem to be in a different cluster. Right? And this happens. Why? Because this happens because in the Minkowski, in the Euclidean distance or Minkowski distance, whatever the distance is, okay, we are adding variables of different units. Can you add year squared and centimeter squared? That makes no sense. Right? That makes no sense. You cannot add years to centimeters. Right? That makes no sense. So we need to bring them all to a standard pedestal. And what is this? The only way we can bring them all to a standard, there are two ways actually. The one way that we all know is standardize. We can do standardize or normalize. What is normalize? Normalize means find the difference from the maximum and divide by the maximum value, maximum minus value divided by the maximum value, or maximum minus minimum. Okay, that's called min-max normalization. So either we can normalize or we can standardize. Yes, Kashif Greaves, if you have a point to make. Okay, I do not know whether I pronounced your name correctly. I'm sorry if I killed your name. But if you see where the moment we standardize, everything is either 0.87 or minus 0.87 in this example. So what happens? Every point is equidistant from every other point. There is no cluster here, or all of them are in the single cluster, or each one is its own cluster. Okay. So the take-home message in this exercise is that whenever we are clustering for all numerical variables, that is variables that contain continuous data, we need to standardize or normalize them. If you are standardizing all of them. If you are normalizing, normalize all of them. Don't do standardization for one and normalization for other. No, do one thing, standardize everything, or standardize or normalize everything. Okay? So this is a way we deal with continuous variables. That's well and good, excellent. How about categorical variables? Do we have to? Yes, Suvir Bajaj, please go ahead.
So, a question. In the previous example, the title of your slide was caution. Now, was this written here because the standardization or the normalization is a compulsion as part of the process, or is an option that you have?
It is a what?
Is it a compulsion, or was it just one of the versions or scenarios that you showed us? Does the data necessarily have to? It's a compulsion. Got it.
It's a compulsion.
Got it. Thank you.
That's because of the formula that comes in here.
Got
You
it.
cannot add time and distance.
Got it.
Professor, I have a question.
Yeah.
In the context of this, yesterday when we were looking at the regularization, the second term had the square of the beta values. Now the beta values will vary based upon whether we have normalized or standardized, and if one of the variable left unnormalized, then that can have slightly a different order of the beta value, and so which means that even for regularization, having them unit normalized to the same range, is it critical?
Yes. See, if you want to do ridge regularization, and if you want to use some kind of a thresholding so that you can do dimensionality reduction, then yes, you should normalize all variables.
But then there is a problem, Professor, because sometimes we create a model based on some criterion, and like we expect that the temperature falls in this way and the pressure, atmospheric pressure is over this range, and so on. But when we start looking at the actual data during the inference time, if it slightly exceeds, then the transformation fails and the model becomes immediately unusable.
That is always the case with every model. All models are valid strictly only in the domain of the data. Domain means the model is interpolating. If the new data is outside this domain, like what you said, slightly different from what we had. If it is outside the domain, then the model is, we should always expect the model to fail. If the model does not fail but gives good results, then that's a bonus. So extrapolation is a very, very tricky process, and we have to take every extrapolation with quite a pinch of salt.
Okay, so there is no model which is capable of extrapolation, or we can use it for extrapolation with a pinch of salt.
Correct. That's correct.
Fine, doctor. Thank you.
Is that why AGI is so impossible?
Say it again.
Is that why AGI is so impossible?
I don't believe in AGI. All this personally, I think AI itself is very hyped up. It's still a glorified next word predictor. Okay, it does a lot of wonderful things. Okay, but still it's just a glorified next word predictor. I mean, some of my colleagues would kill me for saying this. We are not even close to AGI. Okay, we only have simulations of some level of intelligence now. We are not anywhere close to AGI. I don't think I will see AGI in my lifetime, and I hope to live for the next 40 years. Okay. Yes. Somebody, Zoom is ready. Is anybody else raising hand? Okay, looks like. Okay, I hope I'm still in the session, because I got a message saying my Zoom is unstable. Or my
You are there very much, Professor.
Okay,
You are there.
fine.
Yeah, we're still hearing you.
Yeah. So see, let me give a small. I'm going to take a detour. You piqued my interest in this particular topic. Okay. What we have as intelligence is something I have a great doubt about. Let me ask you a question. Okay. This is my personal experience. My mentor, his name is Vengu. He is a faculty at University of Toronto, and also has a joint appointment at University of Michigan, okay, Wisconsin, and Wisconsin or Ann Arbor, Michigan. Yes, okay, Ann Arbor. So now this person has an enormous, I might not be able to say has, at least had. No, age always takes a toll on people. This person had an unbelievable memory. Okay, like the famous Sheldon eidetic memory. So this person had such an enormous memory. Say, for example, I would bring up a question about something. Okay, and then he would say, in this book, in this page, you would find the answer to that, and it would be there, perfect. Okay, so this fellow was such a great memory, had at least great memory. Now, I always wondered, when he gives intelligent answers, I used to wonder whether he was actually using his intelligence, or he is just picking things from his memory, putting them together. Okay. You can ask the same thing about LLMs. Okay. And of course, I know this person is very intelligent, extremely intelligent. I remember one instance where I had an extremely complex mathematics, algebra, where I did about, what was it? 5 by 5 matrix. I have 5 rows, 5 columns. No, 7 by 7. 7 by 7. 5 of these matrices, 7 by 7. Each matrix is 7 by 7, and I have 5 of them, and I was multiplying them. Okay, and I wrote it up as a paper for some calculations, and then I gave it to him for review. Okay, this person did not even do any calculations, verify anything, and he started circling wherever I had made algebraic errors. he could do. And when I went back and test verified, he was spot on. So very intelligent. So now the question is, whenever this person gives me an answer, is the person actually just picking from his memory and just putting them together and answering, okay, in a very abstract manner? Just don't think about, like a Lego. It's not like that. In a very abstract manner. Or is the person actually synthesizing information? The same thing you can ask about LLMs. Okay, it's such a dishonor I'm doing to my mentor because I'm comparing him to an LLM. Okay, but think about this. Let's take another very simple example about LLMs. We find this AI to be so powerful, so this thing, that thing. But take a step back and think about it. You understand that it's just a tool. Let's ask a question. How many books would LLM, let's say you are building a new LLM model, okay, from scratch. How many books would an LLM need to read, okay, before this LLM can write an essay on a cow, let us say? Okay. Compare that to how many books a human being would have had to read before this person is capable of writing an essay on cow. I would bet it would be the difference, the ratio would be in the order of at least thousands. Okay, a child aged 8 or 10 might be able to write a rudimentary essay on a cow, and the child might have read in its lifetime, okay, a few dozen books, whereas an LLM, to reach that level, would have scraped through everything on the internet, would have scraped through the entire Library of Congress, okay, before it could find anything meaningful. Okay. So if you compare this kind of the enormous differences in the abilities of true intelligence and what we actually call artificial intelligence, you really start to wonder whether it's actually intelligence or not. Okay. I strongly believe we are not yet there in the intelligence domain. Okay. We are still in some kind of a weird simulation world only. That's what I am leaning towards. I used to think this is truly intelligent, but nowadays when I think deeply about it, I'm thinking that we are still in the phase of intelligent simulations of intelligence. Okay. And AGI, in my opinion, is far away. Whatever Elon Musk or what is his name, that OpenAI, Sam Altman, or even Dario Amodei, Darius, right? Dario Amodei. Okay. All these people are scaremongering, in my opinion, and they are just after selling their products. But AGI, in my opinion, is very far away. That's my considered opinion. You don't have to agree with it. Sometimes we can debate on that. I don't even agree to artificial intelligence. I don't even agree to intelligence in the phrase artificial intelligence. And just I thought I would pique your interest in these two domains, namely true intelligence, the intelligence of a baby. Okay, compare it to the intelligence of the most sophisticated AI within course that we have now. No comparison. The baby beats this so-called AI in many domains. Okay. Well, anyway, so when you talk about categorical variables, okay, we will talk about two things. There are two types of categorical variables. There are actually three types of categorical, or specifically, predominantly two types of categorical variables. One is nominal variables, right? Nominal. What is nominal? That just we give just names. Okay. For example, different countries, the US, Mexico, Canada, Iran, Russia. Okay. So different countries, those are nominal. So if you want to compare two people in a group, and if these people come from different countries, so they are from different countries, that's all, right? Likewise, there could be other kind of variables where there is some order in the category. For example, you have two people and you are looking at the highest educational qualification. It's still categorical, higher secondary, a college degree, a postgraduate degree, doctoral degree, let us say. So these are different categories, but there is an order. Okay? So we need to deal with these two things separately. And how do we deal with them? For example, with nominal variables, we will try to convert them into binary variables. How can you do that? This is like one-hot encoding, right? If you have only 5 countries, each person belongs in only one of them. So we have 5 countries, 1 0 0 0 0 0 0 0 1 0. Yeah, that's all. So whichever country this person belongs to, put 1 there, otherwise 0. So whenever we can create binary variables, whenever we are able to convert variables into binary variables, we will do it. And then to find the difference between these two variables, between two data points in these variables, we will use what is called Hamming distance. Hamming distance formula is given here. And if you look closely, this is nothing different from Manhattan distance. Okay, there's nothing different from Manhattan distance. Manhattan distance for binary variables is called Hamming distance. Okay, why? What did Hamming do? Hamming did some very interesting observation. Okay, if you have 2 data points, A and B, and a few variables in which they differ, few binary variables in which they differ, okay, and if you find the distance between them using Manhattan distance, what will you find? Here is an example. What will you find? 1 minus 1 is 0, 0 minus 0, 1. 1 minus 0 is 1. 1 minus 1, 0, 0 minus 0, 0, 0 minus 0, 0. 1 minus 0 is 1 again. 0 minus 0, 0. 0 minus 1, absolute value is 1 again. And 1 minus 1, 0. So essentially, if you do the Manhattan distance, all we are doing for binary variables is count how many of these variables, on how many of these variables these 2 data points are different. In this example, these 2 data points are different on 3 variables. Therefore, we don't have to do this calculation. Just compare. No, comparison is much faster computationally than doing this, taking the absolute, then taking the negative sign and then adding them all. No, too many processes to do. But comparison is, are they equal? If they are equal, the value is 0. If they are different, the value is 1. That's all. Find how many of these variables on which they are different, and that is the Manhattan distance between these 2 data points. That's what Hamming observed. In this case, the Manhattan distance is 3. It's a very powerful observation, computationally extremely useful observation, right? So here is an example of seeing what Hamming distance is. Okay? So we have a few 4 variables and some data for each of these variables. Now we want to ask you, the question that we want to answer is, are the 2 movies of Robert De Niro similar to each other, or the 2 movies of Cary Grant? Okay, or 2 movies of James Stewart, whichever way you want to ask. Here we have taken this question. So what do? These are all categorical variables. Okay, and we can do on how many variables they are different. They are different. That's what we are looking at. Nothing else is important. So let's take Robert De Niro. Okay. On the movie dimension, they are different. 1. On the director different distance, on the director dimension, they are different. 2. Actor dimension, they are the same. 0. Genre different dimension, they are the same. 0. So the Manhattan distance or the Hamming distance between the two movies of Robert De Niro is 2. Whereas for Cary Grant, if you see, movies different, directors different, actors not different, genre also different. 3. Okay, Hamming distance is 3. So the shortest distance is for Robert De Niro. So Robert De Niro movies are similar to each other than Cary Grant's movies in this data point, in this data set. I'm not talking in general, in this data set, right? This is how we use Hamming distance. So use Hamming distance when the data is binary categorical data. Okay. Now, life is not so simple. Obviously, people came up and said, okay, let's take about, let's take some real situation where we are talking about a lot of variables. Okay, let's take a retail store. I want to see whether two customers are similar. Okay, a retail store, there are a few things. No, let's not. I'm not going to be worried about their age or those kind of variables now. Let me just look at the items that they bought. That will tell us whether they are similar or not. But then think about this. There are 5,000 items in this store, right? So how do we now deal with that? Okay. So you have to do all these comparisons. So what people came up with is, let's do some other calculation. Okay. Let us see how many variables, on how many variables they had, both of them had 1. On how many variables both of them had 0. On how many variables customer A had 1 and customer B had 0. And on how many the customer B had 1, customer A had 0. Okay. This will give us a much richer picture than just doing a Hamming distance. Okay. This is what people came up with. Okay, that's fine. Okay, this is good. So where all are they similar and where do they differ? Where they are similar is this diagonal, and where they are different is this cross diagonal, right? Cross diagonal. Now, people came up with this idea called simple matching distance. Simple matching distance, which is, it should be actually non-matching distance, because they are looking at what is the proportion of items on which they differ. Right here in this case, differ. What is the proportion of distance on which they differ? And this happens to be, in our case, 3/10. 3/10. Okay. So this is people call it simple matching distance. It should be simple non-matching distance, but the sort of simple matching distance, that's what people called. Okay. They differed. Okay, that's 0.3. And then somebody came up with a different number, a complementary number to simple matching distance. It's a proportion, right? The complementary of this proportion is called simple matching coefficient. Okay? That is 1 minus 0.3, which is 0.7, right? Which is 0.7. So we use simple matching distance for, instead of using the Hamming distance directly, we could go ahead and use simple matching distance. That is a suggestion that people started using. But then a statistician by the name Yakard, he made a very, very powerful observation. What is the observation he made? He said that, let's look at a retail store kind of a scenario. Okay, and if you look at now any customer, okay, the retail store has 10,000 items, 5,000 items, and every customer, okay, even in his or her lifetime, they are going to buy only about 100 or 200 of these items. Not a that is very small proportion of the items is what they are going to purchase. Okay, now among these two, okay, so if you arrange these items in some order, I would have bought 100 items, another customer would have bought a different 100 items. So you would say that our we are differing around 200 items out of 10,000. The proportion is very small, right? That's 0.02, right? 0.02, that's our proportion. So we don't differ at all. That's what simple matching distance would tell us. Very small difference, but actually they are very different. These two customers are. So what Yakad said was, we should not worry about the entire set of variables. We should only, okay, where both of them are zero, where both of them are zero, where both of them did not purchase in this case, we should not worry about that, because the majority of the variables belong in the category. In a real life situation, this number D will overwhelm everything else. Therefore, using D in the denominator would be absolutely ridiculous, is what he said. So he corrected the simple matching distance by dropping D from the denominator. Okay, where did they differ? Divided by the union of the two customers, A plus B plus C, A plus B plus C. Okay, so this is what Yakad came up with, and this is, as you can see now, for example, in these two cases, even if these two customers had disjoint purchasing, okay, 100, so 200, and they, out of 10,000, 9,800 belong in this category D. So we drop that. So among these two, no, they had 0 divided by 200. Okay, 0 divided by 200. Right. So they have, sorry, they had how much? 200. All the 200 are different. Right. All the 200 are different. So 200 divided by 200. Here, 1 and 1 will be 0. This will be 100. This will be 100. So 200 by 200, 1. Their Yakad's distance is 1. That's the maximum you can get. Right. So they are absolutely different customers. Okay. When all of them are in the category 1, okay, then we have A is in the denominator, B and C are 0, then this will be 0. When they are very similar, when they are exactly similar, Yakad's distance will be 0. When they are disjoint, the Yakad's distance will be 1. So this Yakad's distance will vary from 0 to 1. The closer the value is to 1, the very dissimilar are the two data points. The closer the value is to 0, the very similar are these two data points. Right? So when we have binary categorical variables or nominal variables, we will always use Yakad's distance to find the similarity between these two data points. Okay? So that is one type of categorical variable. Now there is another type of categorical variable. Of course, you can define Yakad's coefficient. I'm not going to talk about that. Yakad's distance is what is important. The other categorical variable that we are interested in is the ordinal variable, where there is some order, like high school, higher secondary, graduate, postgraduate, doctoral, or very very poor, poor, okay, good, very good. Okay, some kind of a ordering. Okay. When you have this kind of data that is ordinal categorical variable, then we use what is called normalized rank. Okay? Normalized rank. What is the normalized rank? You give the highest value to one of it. So you give values like 1, 2, 3, 4, 5 in some order, in the order, right? Now what you do for each data point, calculate this. What is the rank given in that data point? Minus 1 divided by what is the maximum rank for that variable? Minus 1. Okay. For example, in this case, let's consider the customer 4. The customer 4 has given poor. Okay. That's the ranking rating this person has given. Poor has a rank value of 2. So instead of here saying 2, what we will do is you will use this for customer 4. What we will use 2 minus 1 divided by 5, which is the maximum rank. 5 minus 1. 2 minus 1 is 1. 5 minus 1 is 4. So 1 over 4, which is 0.25. So we will have for customer ID 4, we will say that that person gave a rating of 0.25 in the normalized rank. Normalized rank, that person gave 0.25. Okay. So this is how we deal with ordinal variables. So nominal variables, binary, done. Ordinal variables, done. Everything else is numerical, done. We use Euclidean distance with the standardization or Minkowski distance with standardization. Okay. So done. Now, what do? We look at real data. In a real data, you expect to find all these kinds of data, right? For example, you might have a person's name. We can disregard that because it has no information. Gender, that's a binary or some nominal variable. Okay. Then you have age. Okay. Maybe you have socioeconomics, demographics value. Then some other categorical variable like how many cars, how many, what is the family size, okay, stuff like that. Then you might have some other continuous variable like BMI, resting heart rate, resting noon time diastolic blood pressure, noon time systolic blood pressure, whatever. So you have continuous variables, binary variables, as well as ordinal variables. You expect to find all of them. In such a situation, what do we do? Which metric, which one of these? Should I use Euclidean distance, or should I use Manhattan distance, or should I use this normalized rank? Which one should I do? Which one should I use? You should use all of them. So what we do is we segregate the variables into each one, segregate all the binary variables, use Jacquard's distance, segregate all the ordinal variables, use normalized ranks, then calculate normalized rank for each one of these ordinal variables. Then you segregate the remaining ones are continuous variables. For them, use Euclidean distance. Find all these distances separately. Then what do? Just combine them. That is called Gower's distance. Gower came up with this idea, or Gower. I think his name is pronounced Gower. At least I remember from the 1980s and 1990s, there used to be this very stylish English batsman, left-hander, in cricket. I don't call batter. The old term was batsman. That's why I'm stuck with this English batsman called David Gower. Okay, yeah, Gower, David Gower. That's what we used to say. Some people say Gower. If anybody watches old cricket, for nostalgia's sake and for some elegance, you can go watch David Gower's batting. Great cricketer. Very, very, what can I say? He kind of embodied to some extent the sportsmanship in cricket. No, he was a great, graceful player. Well, anyway, so separate out each type and then combine all of them together. Okay, combine all the distance using Manhattan distance. That is, you just combine them, add them without doing any squaring or taking square roots or anything like that. Okay, that's what Gower's distance is. Okay, so now we know how to find distances between 2 points, but still we have not answered the question: how do we find the clusters? How do we find the clusters? This is a very simple algorithm, very, very easy idea. Okay, so we'll take a short break. The time on my watch is perfect. It's about 8 o'clock. So we will take a 10 minutes break. We'll be back at 8:10. And when we are back, we will talk about how to use this distance to actually cluster, do the clustering. Okay, and then how to evaluate whether the clustering we got is good or not. We will do these two things. After we come back, with that, clustering will be over. Okay, so short break, 10 minutes break. We'll be back by 8:10. Okay. Now we are ready to do the clustering because we now know the main tool that is needed to do the clustering, namely distance. Okay. So we are going to start with an algorithm called k-means clustering. Here means stands for centroid. So we have k centroids. That means we have k clusters under center point. Okay. This is the idea. Okay. So we will start with a simple example. Of course, as you see the diagram, it will become very clear that it's contrived. Okay. So we'll take the same example like the one we started with, purchases and satisfaction. Okay. Purchases on the x-axis and satisfaction on the y-axis. Both are standardized. So both of them go from -3 to +3. Okay. So here is the data point of 100 customers. Okay. There are a few customers who had high purchases but gave low scores on customer satisfaction. Few have fairly decent purchases and gave high scores for satisfaction, and a few who had a low purchases but still gave fairly high score for the customer satisfaction. Okay. Now, this is the data. This is a scatter plot of the standard scores of purchase and satisfaction, customer satisfaction. Now, what I do is, I have decided that I want to split this into 3 clusters. Okay. So k here, I'm going to set k to be 3. Okay. And what do? I have no starting point. So what I'm going to do is, I am going to randomly select 3 points as the centroid of each of these 3 clusters. Okay. That is, I have randomly selected 3 points: red triangle, red, orange, and blue. Okay, red, orange, and blue. What are these? These are 3. This red is the centroid of one cluster. Blue is the centroid of a different cluster. Orange is the centroid of the third cluster. This is what I am starting with, random selection. Then what do I do? What I do is, for each point in the data, I find which centroid that point is closest to. So let's say this point here, this point here. That point is closest to red. Then I will assign this point to the red cluster. Okay. And this point here is again closest to red. So I'll assign this point to red. Okay. This point here is closest to orange. Therefore, I will assign this point to orange. Okay. Whereas this point here, I do not know right now, okay, but maybe it's probably, or this point here. Okay. This seems to be equidistant from blue and orange. Maybe closer to orange, I do not know. So we will calculate. For each point, we will calculate, we will determine which centroid is closest to that point. I will assign that point to that centroid, to that cluster. Okay. So that's all I'm doing. Very simple idea. So when I do that, this is the clustering I got. Okay. I hope you are able to see these orange circles clearly. So these are the points that belong in the red cluster. These are the points that belong in the orange cluster. These are the points that belong in the blue cluster. Yes, Prince Dubey, go ahead.
That there could be a chance where a particular data point is having an equal distance between the two centroid. Then how we would decide that it should be the part of orange or a blue centroid?
Yes. In that case, if it's exactly equal, then there are 2 ways to deal with it. You could set that point as an outlier. does not belong in any cluster, or you can do a random toss and based upon that you can assign to one of the two clusters. Both are equally applicable.
Okay, so it means either randomly I can assign any of the centroid to that point, or I can neglect it.
Yes, that's correct.
Okay.
Now, if you see this particular clustering, obviously even visually it's clear to us that it's not clean, right? Of course, all these orange points, we have the intuitive idea that they should actually be blue, these orange points. Likewise, these orange points, I assume they should be red. Yeah, I might be wrong, I might be right. So how do we know that we are done? We do not know. So what we do is, and find the mean point, that is mean of all the purchase values, mean of all the satisfaction values for these red points, and that will give the centroid of this red cluster. Likewise, calculate the centroid of these orange clusters, calculate the centroid of this blue clusters. When I do that, this is what I get. Red centroid. Now you see they are very different now. They have moved. The red centroid, the orange centroid, the blue centroid. Now repeat the process. For every point, find which centroid is closest to it and assign that cluster to that point. Okay. So when I do that, when I repeat that step, okay, I get this kind of a cluster. Okay. So you see the red cluster has changed, the orange cluster has changed, the blue cluster also has changed. I do not know whether I should call it orange or yellow, whatever the color is. Now, again, find the centroid of this. Okay. Again, find the centroid of this. Once you find the centroid, repeat the process. For each point, find which of these clusters is closest to it and assign it to that cluster. When I do that, I get this. I get this. Okay. And now I can calculate the centroid. This is what I get. And now I repeat this again. When I repeat this again, nothing changes. When I repeat this, nothing changes. Okay. So I know that I have reached a perfect clustering in my data. Okay. So these are all the blue cluster, these are all the red cluster, these are all the orange cluster. Okay. This is how k-means clustering works. Very simple idea. That is, start with assumed centroids for each cluster. Find for each point which cluster that point belongs to by measuring the distance of that point from the assumed centroids. Okay. And then once you have done this, you have now got k clusters. Now find the centroids for each cluster and repeat the process until you get stability in the clustering. Once you have obtained some stability, stop, you are done. Okay. So that's all. That's all. K-means clustering is over. Okay. Yes, Rio Leong and someone else. Please go ahead.
How do we decide on how many clusters?
That's the next point.
Thank you.
Yeah, from the diagram, the clusters look like circles.
In this,
They look like circles.
yeah, I
The
told you, right? It's a contrived example. So what I had done was, I had assumed these three centroids. Okay, first, this is how I generated these points. I assumed these centroids, and then got certain number of points within a radius, random points within a radius. Okay, so that's why we got this kind of cluster. Okay, so it's I did this randomly, created these clusters and then demonstrated the clustering to you. But in reality, it will be different, right? In reality, data will be much more noisy, and the clustering may not be so clean like this.
Okay. Okay.
So how do we fix the value of k? K is a hyperparameter, which means you will have to vary k from k is equal to 2 to whatever k is equal to 10, 20, 30, whatever. And then for each k, you have to calculate something and use that to fix the optimal k. Okay. So how do we find the optimum k? So we calculate something called within group sum of squared error. What does that mean? Let me go here. In this red cluster, okay, I find the distance of each of these points from the centroid. For the red cluster, okay, I find for each point its distance from the centroid, square that. That will be squared error. Now sum all of them. Sum all of them. Okay, so this is, so I find the sum of squared errors for this red cluster. That's one. Repeat the process for yellow cluster. 2. Repeat the process for blue cluster. Now I have 3 sum of squared errors. One for cluster 1, one for cluster 2, one for cluster 3. And add them all together. And that quantity is called within group sum of squared errors. Mathematically, it's given like this. Okay. For each group L, you have the centroid. For each of the centroid, find how far that point in that group, how far is that point from the centroid. Okay. For each point, square and add them all for all clusters. Okay. This is what sum of squared error. Within group sum of squared error. You have to pay close attention to the subscripts. IL. Okay, L is the cluster number, which cluster it belongs to. J tells you that sorry, K is the cluster number. So J L is equal to 1 to P. 1 to P. No, this is not correct. This has to be changed. Let me do this. Okay. For each group, you have, if let's say J is the cluster number. Okay. That's all we need. Xj is the cluster number. Okay, and squared. And then in that cluster, I'm sorry, this is correct. J. Okay, sorry, I forgot this. Okay, there are P dimensions. There are P dimensions, right? Customer satisfaction and the purchases. 2 dimensions in our case. For each dimension, you have the mean for that particular cluster. Okay, that is your capital X. Then for each point in that cluster, in that dimension. Okay, so you get this. So for each point, you have to find the distance from the center, and then you add them all up, and then add all the values you got for the clusters, like I said. Okay, or simply, what I meant was that for each of the red points, find the sum of squared errors. Errors are measured with respect to the center. So distance squared, add all of them for the reds. That's the sum of squared for red. Likewise, sum of squared error for yellow, sum of squared error for blue. Once you have got these 3 sum of squared errors, add them all up. That quantity is called what happened? That quantity is called the within group sum of squared errors. So as you change the number of clusters, you calculate the within group sum of squared errors, and that plot is called the scree plot. Scree plot. And it looks like this. It will usually look like this. So you see where it's like the folded arm, right? See where the elbow is. In our case, the elbow seems to be at 0.3 at cluster solution 3. So we can take 3 as our optimal cluster. Why? It's very simple. To the right of it, the change is very minimal. So probably all of these points are equivalent. Whereas to the left of it, the change in the within group sum of squared is very high. Therefore, these are all probably equivalent and these are not. Therefore, I take this point as my optimal solution. Okay? So you draw the scree plot, find where the elbow is, and use that to define your optimal cluster. Okay? So this is how we determine the K. So we answered both questions: how to do the clustering, then how to identify how many clusters. That's also done. Okay. John Sirani, if you're asking a question.
Yes, sir. I just want to know, for example, in the past we used this P cases, is it? So there also we use the same formula as x minus x1 minus x2, and then we add it. So yeah, it is the same or it is a different one? We use this for the distance calculator, is it?
It's the same thing like a distance calculator. Sum of squared. It's the same as a distance calculator.
Yes.
Because this
so
is the elbow method. Yes.
Okay. Thank you, sir. Thank you.
Okay. One of the things I'm going to say, very important thing, that K-means clustering has some problem with it. Okay. The problem is that the outliers have significant effect on the outcome. Okay, so when things are equally distant from 2 points, 2 clusters, how things go, depending upon what we use, whether to drop them or whether to include them by a toss of a coin or some kind of randomization. Okay, and that's going to change the way things happen. That's one thing. Okay, if that is the case, if you have outliers, instead of using mean, we can use median. And for the scree plot, instead of using the sum of squared errors, we could use a sum of absolute difference. The sum of absolute difference. So those are the 2 things we would do. And the final cluster that we get in K-means clustering actually is dependent upon the initial guess. It might not be obvious in the example that we did, because in the example that we did, I had created this data with explicitly different clusters. But in reality, it's not going to be the case, and therefore the initial guess of the centroids is going to affect what we finally end up with. So every time we change the initial guess, every time we might get different clusters. That's useless, right? So we need to overcome that. How do we overcome this particular problem? This particular problem, how we overcome is using this idea of farthest distance in the initial guess. Okay, so I'm not going to go through the points that's written here, but I'm going to go to the data point and explain exactly what we are going to do. Okay, so you have this data, and you start with one initial guess, one initial random guess, whatever it is. Okay, one initial random guess. Let us say this is what my initial random guess. So for one centroid, I'm not even going to call it centroid, some initial random guess. Now what I'm going to do is, I'm going to find the point which is farthest from this initial guess. I'm going to find the point which is farthest from the initial guess. If there is more than one point, then I'm going to randomly select from that. Okay? Yes, Prince Dubey.
Sir, maybe my question does not exist into the real world, but is there any chance where the centroid that we selected, right, can have the possibility that all the data points are equal, or are sitting on the equal distance with that?
Possible.
So how we would deal with that problem then?
Okay. So all the points are going to be equal distance from the centroid. When can it happen? Think about this. This can happen only when all the points are sitting on a sphere. And you happen to choose the center of the sphere as your centroid. Otherwise, it's not at all possible. Yes, John Sirani.
Yes, sir. So this is again the number of clusters, and also what Prince is also referring, how we are trying to define like the good clustering in the sense this, in the earlier you mentioned about this, what you mentioned, within cluster, the sum of squares. So we are trying to reduce this value. So then only all the points are nearby. Then we can say
no. See, the idea is this. In this particular data set, for example, let's say if you had only two clusters, okay, one cluster somewhere here and one cluster somewhere here, one centroid somewhere here, one centroid somewhere here, only two clusters. Now you will find the sum of squared errors. Okay, this has a large sum of squared errors. This probably does not have that much. Okay?
Yeah, looks like.
So within two sum of squared errors is large. But now if you move to three clusters, this has a small value, this has a smaller value, this has the same value, and the sum of all these three will be smaller than what we had in the previous case. And if you go to four clusters, I do not know where the fourth cluster might come here. Okay, here is one cluster, here is one cluster, here is one cluster, and then here is the fourth cluster. Okay. Again, if you see, these points are much closer to each other with respect to this centroid here. Therefore, the within group sum of squares is going to still reduce.
So we are trying to always reduce this.
We are not trying to always reduce. It is going to always reduce.
I understood that. If you apply this algorithm, thank you, sir.
Yeah. So now what we are going to do is we are going to start with a random point and then find the point which is farthest from this random point. Okay, and mark it. We will call this as the guess for the first centroid. We repeat this process. Now with this point, now we find, see, this point now is in the data itself. Initially it was not in the data. Now it's in the data. Now from this, in the data points, you find the point which is farthest from this. It could be either this point here or it could be this point here. I do not know. But once we calculate it, it comes out. Okay, this is that point. This is the farthest point. Now of the remaining data points, find which is the farthest from this, from the second one. So that would obviously be this third one. Okay. Now I want to do 3 means clustering. And now what I do is repeat k-means clustering process. Find for each point which is the closest to centroid and assign that cluster to that point. Okay. So if we do that quickly, slowly, quickly, what we will do is, or stably, every time you do this, you will get the same starting points, and every time you will end up with the clusters that you will end up with. Okay. So this is called k means plus plus. Plus plus here denotes that we use an algorithm to select the initial guess also. To select the initial. So essentially, from the boundary, from the extremity in the data set, we are coming inward such that we find the clusters that do not overlap And since we are coming from the extremities, it's going to be stable. Every time we repeat this, we are going to get the same kind of cluster. So this is what K means, plus clustering is. Okay. I'll wait here for a few seconds before moving on to a next algorithm, a slightly better and different algorithm. K means clustering is very useful, very intuitive, very easy to understand, but it's not the most powerful of techniques. Okay. There are two other techniques which are much more powerful, and one of them is called hierarchical agglomerative clustering. Yes, Prince Dubey, please go ahead.
As you just mentioned that this is a powerful algorithm as well, but I see a problem with this algorithm is that in case if my data set is very, very big and very much into high volume, then calculating the distance from one data point to another data point, because here it is actually, making a calculation on each data point from a single data point to all other. So
let's make it simple. If you have 10 million data points, and let's say if you want 10 clusters, okay, then you are doing 100 million distances.
Yes.
Okay. Yes, correct. So it
is going to consume a lot of compute and storage as well.
Very true. Very true. It's a computationally intensive problem. If the data is academic, okay, not too large like what we are talking about.
Okay. So can we apply this? So in case if I want to replicate this on my machine, on my personal machine, do you think on a moderate set of data it will be fine, right? It won't give any problem.
Yes, a few thousand, few 100,000 might not be a problem.
Okay.
No, a few 100,000 might, a few 100,000 might not be a problem. But then as you increase, you remember to identify the proper K, you are going to repeat this process for a large number of Ks. And that means that's again an added dimension to the compute. Right. So it is computationally heavy. Okay. So a better algorithm is what is called hierarchical agglomerative clustering. Okay. Now, what is this hierarchical agglomerative clustering? I'll again start with a simple example and explain this. Okay. I'll leave this descriptors to you. You can go and read. Okay. Here's a. So what we do is we start with all the points. Let's say we have the 6 points A, B, C, D, E, F. It's 6 points are there. Now what we do is we find pairs of points that can become clusters. Okay? Identify pairs of points that can become clusters. So in this situation, we see A, B, and D, E. They have the same distances. Okay? So they become, AB becomes one cluster and DE becomes one cluster. Okay? So well and good. Now what we do, we find the slightly bigger cluster. Okay, what is it? Now what we want to do is we treat AB as one data point, DE as one data point. Now do the same thing. Find pairs. Okay. So in that situation, then what you have, A, B, and C become one cluster. That's the smallest distance. Every other distance is slightly larger. So this becomes the smallest distance. We make this as a one cluster. Then again, we repeat this. You treat this as one point. So we have 3 points, 1, 2, 3. Find the pairs. In that situation, D, E, and F becomes a cluster. Okay. That becomes a cluster. Now we have 2 points, and that becomes a cluster. That is, everything is one cluster. So what have we done? We started with individual points. We kind of, at every step, we are kind of doing pairwise clustering. Okay, we are finding pairs of points that become clusters until we reach a situation where every point is in a single cluster. Okay, so what? Now what we do is, okay, now as you can see, the same thing can be drawn in a diagram like this, in a what is called a dendrogram. Dendrogram. I think it's called dendrogram. I'm not sure. It's not sure if it's dendrogram or dendrogram. Okay? It comes from dendrites, which means branches. Okay? It probably should be dendrogram. I'm not sure. Somebody find it out and let me know.
Yeah, it's dendro. There's a R missing. Dendrogram.
It's a dendrogram. How do we draw the dendrogram? We are drawing it in terms of the similarity. Okay, the similarity, that is, it's going in this direction. Okay, so you plot for each of these points. We club them, okay, based upon the similarity. Okay. AB is similar with the same amount. DE is also similar, so we club them together. Okay, and then the next step, AB is similar to C. The similarity is at this level, okay, at a higher level. Okay, that is similarity. Similarity. It's not the distance, so it's the reciprocal of the distance. A similarity is low, distance is high. Okay, so that's what it is. And the next step, find the next level here, D and F, and then all of them. Now what we can do is, we can set a threshold on the similarity. You remember, now you see we are kind of doing something like going from overfit to underfit, right? So now what we can do is, we can set a threshold on the similarity, and at that threshold we find what are the clusters we have. So here is a threshold I have set here. Okay. Then I see I have 3 clusters. One cluster contains ABC, another cluster contains B and E, another cluster contains only F. Okay. This kind of approach is called hierarchical agglomerative clustering. We are going in a hierarchical manner. We are agglomerating, right? We are adding points together, and we are finally arriving at the clusters that we want to get. So this is called hierarchical agglomerative clustering. Okay. So that's all. The algorithm is, that's all. Very simple algorithm. Okay. But then remember, I told you treat AB as 1 point, DE as 1 point. How can I treat 2 points as 1 point? Okay. And this is where the catch is. what I can do is, I can find the distance from A to B, A to C, and B to C, okay, and use the minimum of them, or maximum of them, or the average of these 2 distances, or I can find the midpoint of A and B, and from that midpoint see how far away C is. Right? So all these multiple ideas are possible. Okay? And each idea has its own name and application, but we'll see there is a much better application, much better idea than any one of these. Okay? So distance between the clusters can be in multiple ways. Simple single linkage clustering. Okay? This is the shortest distance between 2 points that are in different clusters. As I told you, okay, find the distance between A and C, find the distance between B and C, find the shortest distance. The shortest distance is B and C. Okay, that's one thing. Now D and C, E and C. The shortest distance is DE, and then FC. Out of these 3, BC is the shortest. So make this as 1 cluster. So A, B, and C will become 1 cluster. Okay. And this kind of approach is called single linkage clustering. single linkage clustering. The next one is called complete linkage clustering, because we are going to now, we are not going to use the shortest distance, but we are going to use the maximum distance. Okay. So let's go back here. Okay. Now what we can do is you can find A, C, B, C. Out of these, the maximum distance is AC. Okay. Then D, C, EC. Out of this, the maximum distance is EC. Then F and C. Okay. Now you have three distances. We have found the linkages using the maximum distance. Out of these three, which is the minimum? Out of these three, which is the minimum? Okay. Again, you would find that AC, that is this linkage, that is the complete linkage that has the minimum. So you cluster them again. Okay. So you are finding the maximum distance to find which are the possibilities, but out of this, all these distances, you choose the minimum. Okay. That is called complete linkage cluster. Then, of course, average linkage clustering. For each points in different clusters, find all these different distances, find the average. That you do for different clusters. And then combine those two clusters, which are the least of the average linkage. Okay, least of the average linkage. Okay, so this is the average linkage. Then there is called the centroid linkage. What is it? Centroid of one cluster, centroid of the other cluster, and find the distance between them. So which of these different clusters have the shortest centroid linkage? Club them, make them as one cluster. Okay. So these are all different ideas that are very easy to visualize. Then there is finally a killer cluster, killer linkage called Ward's method. What Ward did was very simple idea. The idea of clustering is to ensure that we have points in the same cluster that are very similar, right? So if you have three clusters, say A, B, C, three clusters, you can have AB or AC or BC, right? We can combine this, we can combine this, or we can combine this. Now, when you combine, you find the sum of squared errors. That's the variance. Sum of squared errors, right? Or sum of mean squared error. Mean squared error. You find the variance, mean squared error, for each of these possibilities. Okay, cluster A, cluster B, cluster C. Cluster AB is one possibility. Cluster AC is one possibility. Cluster BC is one possibility. Find which of these combinations has the least variance, least increase in the variance. Initially, it was something. Initially, there was some variance. Now, when we combine, the variance increases a little bit. Which of these combinations increases by the lowest number? Which increases the same way lowest number? Use that. And this is actually directly talks about what we want to do with clustering. What we want to do with clustering, we want to have points that are similar to each other. That means the variance among these points should be small. And that's what this is doing, Ward's method. Okay. So Ward's method is probably the most reliable and direct to definition kind of linkage that we do. Okay. So each one can give different. So here's an example. For each one can lead to different kinds of clustering depending upon the data set. Okay. Here is a data point we are looking at 1, 2, 3, 4, 5, 6. You know, it looks like a plus in some crooked sense, right? So now let's see how these different things work. Okay. A single linkage actually gives this kind of a clustering. Single linkages, you find the shortest you find the shortest distance between points in two different clusters, right? That's single linkage. Complete linkages find the maximum distance. You see, single linkage and complete linkage, they are quite different. 5236, that's fine. 521, 346, but here it is 5236 together as one group, and then 52364, and then everything else. Okay? Likewise, if you look at group average linkage, it's different. Average linkage and complete linkage, they seem to be identical. They seem to be, but not. You see that 521, 364. Okay? But here 52364, and then 52364, and then 1. There's always some difference between these different methods. What's clustering? You see 5236, 364, 1346, and then all of them. Everything will have slightly different types of clustering. Now, if you look in the dendrogram, again, I think it should be dendrogram. Okay. Now, what you can do is, this is how the dendrogram looks for the different types of linkages. And then obviously, you can set a threshold, okay, and then use that threshold to see what is your optimal clustering. In fact, by changing the threshold, for every value of the threshold, you can, or every value wherever you set, move this from the lowest value for similarity. Sorry, this is in the distance scale now. From the lowest value of the distance to the highest value of the distance, you change it systematically. As you change it, calculate the sum of within group sum of squared errors and see where you get the lowest value, or you see the scree plot and then use that. Okay, and this is how you decide how to do the clustering in a hierarchical agglomerative clustering. If you are just using Watts clustering, you don't have to do all completely here. No, you do one set here where the first two are clustered, and then these two and these two are clustered. You calculate, you cut here and get your sum of squared errors within group, and then here, and then here. Where only a few calculations you have to do, and then you determine what is your best cluster that you can get. Okay? And this is the way we use hierarchical agglomerative clustering. Very simple idea, very easy idea. Okay? Yes, Suvir Bajaj, please go ahead.
So what is the purpose of using hierarchical agglomerative clustering? Like, what is the real world use case?
Addresses the computational complexity that Prince Dubé expressed earlier. Even though this looks a little bit more complicated algorithm than k-means clustering, okay, the actual number of computations done is slightly less. Every time when you agglomerate, the number of calculations you are going to do actually goes down. Okay, whereas in your other case, it goes linearly, but in this case, it doesn't grow linearly. So that's one of the advantages. Okay?
Got it. Thank you.
So in most large data sets, people don't even use k-means clustering. They go directly to hierarchical agglomerative clustering to save time and compute. Then there is the final final type of algorithm, the third type of algorithm, which is a very, very powerful and very useful idea. And this algorithm is useful even when you have when the data is so complex, okay, that you don't even know where to start. Okay, so what does it do? The DB scan stands for density based scan. So what we are going to do is we are going to scan the entire feature space using the idea of density of points. Using the idea of density of points. So you know what is density, right? Density is, for example, for when you're talking about density of an object, that means mass per volume, right? So if 1 liter of water weighs 1 kg, then we say that the density of water is 1 kg divided by 1 liter. Okay, that's the density. 1 liter is what, 1000 cc, 1000 cc, right? So that's the density of water, 1 kg per liter. Now, if you have not water but heavy water weighs 2 kg per liter. Therefore, heavy water has it depends upon whether it's purely deuterium or if it's deuterium plus tritium. So maybe a little bit, slightly more than deuterium. Okay, so maybe a little bit more than 2. So that's how we calculate density for objects. Likewise here, we choose a volume. We choose a volume in the feature space and find how many data points are there. Okay, that's all. We are going to count how many data points are there. Okay, using this idea, we are going to scan the entire feature space and then identify clusters. How are we going to do that? So the volume, here I say area, I say area because I'm going to demonstrate on 2 dimensions, but in 3 dimensions or multiple dimensions, imagine a volume, a sphere. So it should be a volume. A sphere of radius epsilon. What is the value for epsilon? Hyperparameter, you choose. Okay. So we consider one point and then consider a small volume around it. And then see how many points are within that volume. Including this point. Okay. If this number is beyond the threshold we set, we call this threshold min points, minimum number of points. Okay, minimum number of points. We set a threshold for the number of points. That is, we set a threshold for the density. Okay. If within this epsilon, the number of points is beyond a threshold that we have set, then we say this point is going to be useful for us. Okay. Otherwise, this is some scattered data, so let's not worry about it. Okay. Excuse me, sorry about this. So how do we set the minimum number of points? The minimum number of points we set to be, if there are p features. If there are p features, then the minimum number of points should be at least 1 more than p. If there are 10 features, then min point should be at least 11. At least 11. Okay, this is a rule of thumb. Okay. Then some definitions. A core point. So you, in the feature space, you choose a point, and we are going to call this point a core point if around this, in the neighborhood, we call this a neighborhood. What is a neighborhood? Neighborhood is the volume around this point, where the volume is defined by that epsilon, the radius epsilon. Okay, so that is called the neighborhood. If the neighborhood of this point contains at least min PTS points, okay, if there are at least minimum of the threshold we have set for the number of points, if this neighborhood of the point contains at least that many points, then that point is called a core point. Okay, that point is called a core point. Definition. Then we call a different point as a border point. What is a border point? A border point is a point which has within its neighborhood one core point at least, but it does not have as many points as we need for core points. Okay. That is, we have, let's say, we have 10, 11, we said 11, right? 11 is the minimum number of points we need, okay, to be called a core point. So this point, we need within its neighborhood, it has only 7 points. But one of those 7 points is a core point. Okay, that is, in that neighborhood of that point, there are 11 points. But in the neighborhood of this point, that core point is here, but it doesn't have 11 points in its neighborhood. If that is the case, that point is called a border point. Every point that is not a core point or a border point is called a noise point. What does it mean? A point in its neighborhood, the number of points is less than what is required, and there is no core point in its neighborhood. If that is the case, it is called a noise point. Okay, so it may be difficult to visualize. So let's take a look at an example. Okay. Here on the right hand side is a circle, that is the area with epsilon. So I'm considering this point A, and I have set min PTS to be 7. There should be at least 7 points in the neighborhood. So in this neighborhood, let us count how many points are there. 1, 2, 3, 4, 5, 6, 7. So there are 7 points in the neighborhood of A. Therefore, A is called a core point. Okay. Now let's come to B. In the neighborhood of B, if you see, there is 1, 2, 3, 4. There are 4 points only. Okay, in the neighborhood of B. But one of those 4 points is a core point. Therefore, B is called a border point. Let's come to C. C has 1, 2, 3 points in its neighborhood. But none of these 3 points is a core point. Therefore, C is called a noise point. C is called a noise point. Okay. So we can tag every point as a core point or a border point or a noise point. Okay, very good. So how do we do the clustering? Very simple idea. Okay. What we do is start with a random point. Start with a random point. You have set the epsilon, you have set your min points. Okay. See whether this point is core or not. If it is not core, discard this point, go to some other random point. Some other random point. Keep doing it until you have a core point. Okay. So let us say you have a core point. You have determined a core point. Okay. So that is, in its neighborhood, you have the required number of points or more. Now from this point, go to its nearest neighbor. The next point closest to it. Okay. Go to its nearest neighbor. And then go to step 2. Determine whether it is core or not. Okay. If it is core, go to a next nearest neighbor. From that point, go to the nearest neighbor, but don't go to the previous point. Okay, you don't go to the previous point, but go to the new nearest neighbor for that point and see whether it is core or not. Okay. You keep doing it. You keep doing it until, okay. In fact, I don't want to say it this way. See whether it is noise. Noise or not. If yes, yes, go step 1. If no, go to its nearest neighbor. Okay. So what you will do, as you keep doing it, you will start you will start mapping all the core points and the border points. Okay, so you keep doing it until you reach a position where you cannot go to a core point. Okay, so now you have identified one cluster. You identified one cluster. Now what do? You don't consider these points in the cluster. Consider all other points and then choose randomly one point in that and repeat this process. Okay, repeat this process. This way, you can find all clusters that are possible. All clusters that are possible. Okay. So let's take a look at this. This is very interesting, this page. Let's take a look at this. Okay. So digital Vidya. So here's the k-means clustering algorithm in action. Okay. And here's the DB scan. Okay. So it's marking all the core and border points. Okay. Once that cluster is identified, it jumps to a different random point and identifies a cluster there. Next one, and then everything else you see, they are all considered as noise points. Okay. Of course, you can clearly see this is again a contrived example. It's a smiley. That's what it is, right? So you keep doing this. So you identify one cluster, then go to a different random point, keep doing this. Okay. So this is how density-based scanning works. It's very, very powerful. Excuse me, give me a minute, please. Now, we have not answered the important questions. Okay, the important question, how do we fix the epsilon? How do you fix the epsilon? That we have not fixed. Okay. Now this is like a hyperparameter, but we can fix it. Okay. So let's go ahead and do how we can fix the epsilon. Okay. Now what we do is, for each point in the data, find its kth nearest neighbor. Okay, kth nearest neighbor. Let's call this the kth distance. Say you can find the nearest neighbor, that will be 1k, 1 dist. You could say the second nearest neighbor, that will be 2 dist. You could have the 10th nearest neighbor, that would be 10 dist. Okay, for each point you do that. Now what happens? For each value of k, let's say we have k set to be 4. Okay, for 4 dist, okay, 4th nearest neighbor, you have different distance values. Different distance values. Sometimes for one point, the 4th nearest neighbor might be this close. For a different point, its 4th nearest neighbor might be this far away. Right? It could be something like this. So you have many distances possible for the nearest neighbors, 4th nearest neighbor, kth nearest neighbor. Now you sort those distances, and then plot. What are you plotting? Okay, you are plotting the distance on the y-axis. Okay, so the distance could be, let's say, some units, 5 units. Okay, 5 units. Okay, how many points in your entire data set has 5 units as the distance? That is plotted along the x-axis. That is plotted along the x-axis. Okay. So for example, in this case, there are 500 points that have the fourth nearest neighbor to be something like 3.5 units. Okay. There are 1,500, there are 1,000 points that have the fourth nearest neighbor to be 5 units. So something like that. So you plot this. This plot also has like an elbow shape with a sharp upturn for some nearest neighbors. Okay. Now, what you want to do is you find the elbow here. You find the elbow here. Okay. So now that elbow, okay, you find the distance corresponding to that elbow and use that as your epsilon. Use that as your epsilon. Okay. How do I fix K? Remember the golden rule, the thumb rule of thumb. If there are P features, take at least P plus 1. So you can set P plus 1 and do this. Okay, do this. And then find that as the epsilon. Find the epsilon for that. Using this idea. Once you get that epsilon, go ahead and solve your problem, dB scan. Okay. So this is the way you fix epsilon for doing dB scan. So for example, K-means clustering or a hierarchical agglomerative clustering will not be able to identify clusters in these situations. Say for example, you have like a ball inside a ball inside a ball kind of situation in multidimensional space. Okay. K-means clustering, hierarchical agglomerative clustering will not be able to do that. Will not be able to identify the clusters, but dB scan will. dB scan will correctly identify these two as two different clusters, but K-means will not be able to do it. Okay. For K-means clustering, this point is closer to this orange point than to this blue point. Same thing is going to happen for hierarchical agglomerative clustering. But we know these are the natural clusters. dB scan will be able to do it. So if you are doing hierarchical agglomerative clustering and you are not satisfied with the kinds of clusters you are finding, then go ahead and employ dB scan, and I'm pretty sure you will get a very good results. Okay. So that's it. 3 basic tools, algorithms in our arsenal to do clustering, and that's all there is to it, to clustering. Okay. In all these cases, clustering is done based upon distance, which is spent enormous time today to understand. And then these algorithms are fairly simple algorithms. And finally, once the clustering is over, we can go ahead and check whether the clustering is good enough, a final test. The final test is done using the ideas of what are called cohesion and separateness. This is what I talked about in the very beginning. Okay. All points in a cluster, they should be together. They are closer to each other than 2 points in the other clusters. The clusters are separated. Both of these ideas are measured by this cohesion and separateness. Okay. Cohesion measures how close the points in a cluster are to each other. Separateness measures how far away are 2 different clusters, essentially. Okay. So what we do is, instead of talking for separateness for individual clusters, we talk for each point. For each point, we find cohesion and separateness. And we define what is called a silhouette coefficient. Silhouette coefficient. So what do we do? So consider a cluster, some cluster, find some point, ith point in that cluster. Okay. Find its average distance from all other points in the cluster. the difference, the average distance from all other points in that cluster. Okay, so that value we will call that AI. We'll call that AI. Okay, this is the cohesion for that point. How close is it to other points in that cluster? So this defines the cohesion of that point. Now, for this point, you find some other cluster. You are worried about some other cluster, a nearest cluster, let us say. You find the average distance of this point from all the points in the other cluster. Okay, for all the points in the other cluster. So this point, this value tells you how separated it is from the other cluster. Okay, we call it the separateness of the point. We give it a symbol BI. It should be obvious that in a good clustering situation, BI is greater than AI. Separateness is greater than cohesion, right? In a good clustering scheme. And this is what we measure by what is called silhouette coefficient. Silhouette coefficient for that point. How do we define? We define it this way. B, the separateness, minus A, that is the cohesion. Okay, divided by the maximum of A and B, maximum of A and B. In real situations, we won't get B, right? If the clustering is poor, then maybe we will get A. Okay, if the cluster is too big, and the next cluster is quite close by, but it's small, that cluster is a small cluster, but this cluster is a big cluster. So its cohesion can be a larger number than the separateness. It's possible for a point, right? So you take this maximum of A and B. Okay. Now this is for one point. This is for one point. Okay. Now what you can do is, okay, think about this in clean situations. SI can be negative, positive, whatever. SI close to 1 indicate, okay, SI close to 1 indicate good cohesion, strong cohesion. Okay, SI close to 1 indicate AA is close to 0, therefore strong cohesion. Okay. Now, what we actually do is to find whether the clustering is good. This is only for one point. Now, what we do is we do it for all points in the data. You do it for all points in the data, then find the average. Find the average. So you find average silhouette coefficient. Okay, find the average silhouette coefficient. Now what you can do in situations like K means clustering, K plus plus means clustering, or K means plus plus clustering, or hierarchical agglomerative clustering, instead of using the sum of squared errors, you could use average silhouette coefficient to see which K gives you the best performance, which K gives you the maximum silhouette coefficient, the maximum silhouette coefficient. Okay, that's what we will use as our best K. Yes, John Sirani, please go ahead.
Rajan sir, this is my short question. I'm not sure whether it is correct or not. For the separateness, we are telling about how far these two groups are separate, is it? But what happens if I have a common parameters, or maybe, I love mathematics as well as I love sports. If I have that kind of data, would that still work with this silhouette coefficient?
No, see, think about this in the problem, okay?
Mm-hmm.
In the problem, how you are going to do is this. Love for mathematics is going to be one axis. Love for sports is going to be another axis.
Mm-hmm.
You are not going to put love for mathematics and love for sports in the same axis.
Okay.
Right? So they become different dimensions in the problem.
Got it.
So your thing would be, if you love mathematics and sports equally, it will be like a 45-degree line. Your vector will be like a 45-degree line somewhere here. If you like sports more than this thing, your vector will be like this. Mathematics, it will be like this. Okay, so that's how it's going to be. Okay. So
Got
using,
it. Clear. Thank you, Rajan. Yeah.
So using this mean silhouette coefficient calculated for all the points, from that you calculate this for each k value in k-means clustering, or for each level of the threshold, and use this as the guidance for choosing the best clustering scheme. Okay, so once you have got the clusters, the problem does not stop there. Only the technical problem has stopped there. Then you go back and look at your clusters and see, okay, what is the common property of this cluster 1? What is the common property of this cluster 2? So on and so forth. Okay, and then you take an action based upon your understanding of the cluster. For example, a few months ago, I was involved in understanding the characteristics of members of a large cooperative. It's a dairy cooperative. They had members who had anywhere from 1 cow to about 10,000 cows. So large variety of members. Okay, and they wanted to see whether they could plan activities for different types of customers. In general, people would blindly go and say small farms, medium size farms, large farms, extremely large farms. People would do something like that. But they had a good intuition that that's not a great way of doing things. We have to create programs based upon the characteristics of the members. So they came to us and we did some. They came to us with some done questionnaire. I helped them refine the questionnaire. They sent out the questionnaires to the members, got the questionnaires answered by survey done by about 300 or 400 members, and then we looked at the responses, and we did the clustering. And you know what we found? The farm size was not a factor at all. Farm size did not come out as a common property of any cluster. What came out, some of the very interesting things that came out were the attitude. Okay, how positive are they about the industry? How positive are they that they are going to grow in the next 5 years? How positive or how much are they thinking about diversifying into different areas? These actually separated their members rather than the farm size. Okay, so sometimes this clustering would give us some enormous insights, something that we have not thought about. Okay, so that is where the real problem starts. Now, identifying the properties and then taking actions based upon this. So usually clustering is only used as an intermediate step. For example, in many situations, okay, clustering can be done as an intermediate step for linear regression. Your linear regression problem itself might have, instead of all your best efforts, okay, you might have got an R squared of only 40, 0.40, 40%. Okay, and you're breaking your head. How can I improve? There is nothing much I can do. No, you can do something. See whether there are clusters in the data. If there are clusters in the data, separate them out. Identify the clusters and build models for each of these clusters. And now you would see your R squared value actually increases, and sometimes dramatically. Okay, so clustering is usually not the end game. It is usually an interim step before we start answering the most important questions for our activities. Okay, so with this idea, I'll stop here today. and wait for any questions. If there are any questions, what we will do is we will meet you. Yes, Leon, please go ahead.
Yeah, just a quick one. In your example just now, would you say that you will choose k-means clustering, or would you use the HAC?
Rio, can you please repeat? I got only chopped question from you.
Yes, the example that you gave just now, would you have used k-means clustering, or would you have used HAC?
Depending upon the data size. Okay, if the data size is quite large, I would definitely go ahead and use hierarchical agglomerated clustering. Okay, for example, if you remember, I showed you the tiny data set, 1033 data points for the compressive concrete strength data. That's a very small data for realistic usages, right? In those situations, I would go ahead and use k-means clustering.
Thank
But
you.
probably in real enterprise situations, we'll start with hierarchical agglomerated clustering directly.
Professor, I have a question. With respect to the assignment 2, right? Is there any coding expected? It is
No.
only about a managerial problem definition.
Exactly. No coding expected.
Okay. And we don't have to look at any existing data set also, right? This is definition of a problem and fitting the problem to a certain the tools, right?
Right. You probably will have to describe what kind of data you have.
Okay.
But not necessarily you have to get a data and do any analysis. That's not required.
So when I'm taking a problem from my own domain and I am, describing what kind of variables I'm having and all those things, I don't have to provide a sample data of that, right? I can describe the problem nature and the kind of variables I'm taking. Okay. And another thing is with respect to the number of words, I have seen that 2,500 to 3,000 words. Now, if suppose some foundational aspects of the domain has to be clarified, and if it is taking some words additionally, will that be penalized?
Yes.
Okay. So
I'll tell you an example from my own experience. Okay. One publication that I'm very, very proud of, that I published with one of my graduate students. It was in a field called amblyopia. I think I mentioned to you about amblyopia. It is a visual deficit when people have crossed eyes. Okay. And usually what is assumed in the clinics is one eye has reduced vision, the other eye has normal vision. And we questioned this. No, we said that's probably not the case. And then we did some analysis, retrospective data. We got about a few dozen measurements from the clinic. And then we did some analysis, got some wonderful results. We wrote it up, and we had initially we had 6,000 words or 7,000 words. The journal that we submitted to, they were very strict. They said it has to be less than or equal to 4,000 words. So what we said was, we kind of refined it without losing the meat of the matter. We came to about 4,200 words. We sent it. The second day, the next day, we got an automatic rejection saying it exceeded our limit. Okay. So when you go to the publication site, this is ruthless. Basically, because they are working on budget constraints. Every increase in the number of word count probably increases their page that they have to print. Okay, and that adds to the cost. All these things are there. So, and then I tell you what really happened. Cutting down that to the 200 words, removing the 200 words, made us read through our paper with a microscope and figure out where are the redundancies, where are this verbal vomit, as I would like to call it, and make the paper tight. And that really helped me. I'm really, really proud of the paper, even though it gets only a few citations. It's one of the remarkable papers in that field, in my opinion. And it brought a lot of discipline to my writing. So I would say that 3,000 words is the hard upper limit.
Sure. Thanks.
Rajan sir, this 3,000 words are after the abstract and executive summary, is it, or that is also counted?
That's also counted.
Okay, thank you.
Sure. Okay, I'm sure now you are all thinking about the assignment. I think the assignment is due next Sunday or so. I don't want to make any correct. Is it due next Sunday?
It's on Friday, next Friday, I